Alright, so this is the recording for lesson 1.03, the other lesson that is predominantly on the 1.05 quiz. This one focuses in on types of matter and types of energy, and making sure you can distinguish those two. So, first things first, matter is something you probably already have an idea of. But matter is anything that takes up space, i.e. it has volume, and it has mass. Alright, so mass and volume. So, a baseball, your computer, water, the air around us. Alright, even though you don't necessarily see it, there are molecules in there. Alright, so those molecules do have mass to them and take up space. So lots and lots of things are matter. Matter is really easy to comprehend because for the most part you can see it. Now, again, probably something you already know, but there are three states of matter that we are going to deal with in this class: solid, liquid, and gas. Things that you may not necessarily have committed to memory about these are the kind of characteristics of them, but you want to know that solids have a definite shape. All right, they have a fixed shape. Your computer is, rectangle, X number of inches wide, Y number of inches long, blah, 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 and that's a fixed size, all right? And this term compressible, as you'll note later, comes in with gases. Solids are not compressible. If you sit there and you try to squish your computer to take up less space, you're going to break it. So don't try that. So examples, things we just talked about. Computer. A block, a tree, bones, right? All sorts of different things are solids. Liquids have a little bit more flexibility in their shape. So they will take on the shape of their container. But liquids also, for the most part, are not compressible. If you sit there and you try to take a container and squish it smaller, the liquid is just going to come out at the seams, or the container is going to burst open. All right, you can't compress the liquid in a container. So, liquids that you're probably familiar with, I hope you recognize this formula for water. All right, you can also think Gatorade, orange juice, liquid nitrogen. All right, so it's not that these things necessarily have to be liquids, it's just I'm talking about stuff where at room temperature they're liquids, because we know we can turn ice into a solid. We can also turn water into a solid by making ice. We can also evaporate it and turn it into a gas, right? But at room temperature, water is a liquid. Now, gases are matter with really no shape. They will fill every space that they have access to. So, like water, if you put a little bit of water in the bottom of a glass, it's just going to sit on the bottom of a glass. If you put a little bit of gas inside a glass and then cover the lid, it is going to spread out to take up the entire space of the gas. And this is where gases have this ability to be compressible. All right, so a gas, if you take, you think about it like a plunger or something like that on your cup, and then you kind of squish it down, the gas will take up less space. All right. There's also, if you take a balloon to an extent, you can squish the balloon and make it smaller, therefore making the gas take up less space. There is a limit to this, and that kind of depends on the strength of the walls of the container it's in, but gases can be compressed. So, gases you are hopefully familiar with. There's one that you breathe out, one that you breathe in. All right, so we breathe in oxygen, we breathe out carbon dioxide. All right, nitrogen gas, hydrogen gas, helium gas, all sorts of different things. All right, so just a couple of quick practice stuff. So I gotta slide this over so I can actually see. Metal mercury flows across a table and takes the shape of any container it is placed in, but will not necessarily fill the container. what state is mercury in at room temperature? So give it a second, see if you can figure out the answer. Pause the video if you need more time. But I'm hoping you are zoning in on the fact that it does move, it flows, it can change its shape, it can fill a container, but not necessarily all the way, which fits in line with being a liquid. And then, what is the defining characteristic of a solid? So, you got choices D, E, and F. Of definite shape, fills all open space, or is compressible. Alright, so definitely solids, we know they have a fixed shape. That's another word for the word definite. So there's that definite shape. These other two, fills all open space and are compressible. I hope you can recognize that those belong to gases. So there's your review of matter. Energy, on the other hand, is something that, again, you probably have kind of a mental concept of, but maybe haven't discussed in a, scientific class sort of setting. So energy is what will cause a change in matter. The tricky thing about energy is that it's not physical. You don't see it. You can't you can't see it, touch it. It doesn't physically exist, but you can see the consequences of it, all right? Or feel the consequences of it. So for example, thermal energy. When thermal energy is causing a change in something, you will notice a change in temperature. All right, so like when you burn something, it gets hot. All right, so that is thermal energy. Or again, if you're starting a fire, radiant energy, giving off light. All right, so that energy is present and you're able to see it as light, but that's just kind of like the after effect of the energy being there. There's also another type of energy called chemical energy, and that is the energy that related to chemical reactions and allows bonds to break and form. All right, and these energies aren't like only one type of energy is involved, especially if you think about a fire, right? You can see the radiant energy or the effects of the radiant energy in the light. You can feel the heat from the fire. And as the objects are burning, bonds are breaking. All right, so all three of those energies are involved in what's going on there. All right, and you know that matter is changing because, if you were burning a campfire with some logs, afterwards those logs are ashes. All right, so just knowing the definition of energy and just kind of recognizing some of the types is good here. But what I really want to focus on with you is this idea of exothermic and endothermic changes. All right, because these can happen with chemical reactions, but these can also happen, say, when you change state. If something melts or something freezes, we do have a change in thermal energy because temperature is changing. All right, so I want to break these words down. The prefixes exo and endo are going to help you kind of remember what these do. All right, so I remember exo meaning out because exo sounds a lot like the beginning of exit. All right, so that's how I remember that one. And then endo, the beginning of it kind of sounds like in. All right, and then thermic, we've already talked about that before. Thermo means heat. All right, so heat is either exiting, exothermic, or entering, endothermic. All right, now, the trick is kind of remembering what direction things go. So when you talk about these things, you're going to have a system. All right, that might be, melting water. Or melting ice. Or it might be a reaction. All right, that's your system. All right, you typically are not the system. All right, and then you're going to have your surroundings. All right, you would feel the opposite of what's actually happening in the system. So these terms, exothermic and endothermic, they apply to the system. All right, so when heat exits the system, we call that exothermic. When heat enters the system or goes into the system, we call that endothermic. You, however, feel the opposite of what's going on, because if heat leaves the system's going to get cold. But you are going to feel that heat because you're in the surroundings, so you feel that things get warm. All right? So, exothermic processes release heat from the system. All right? The surroundings get warmer. So if the surroundings are getting warmer, then that means the system is getting cooler, and that's exothermic because it's losing its heat to the surroundings. So some obvious examples of this are like a fire. You guys feel the heat. But what's actually happening to the log is losing that heat, and that's why you're feeling it. Some not so obvious examples is something like freezing of water. All right? Because I know we're used to the idea, oh, freezing water, I get cold, blah, blah, blah. But really what it is the water itself is getting colder. All right? For water to freeze, it must get cold, which means heat has to be given away. The reason why we feel cold, say if you're inside a freezer where the freezing takes place, is because we have to actually give the heat somewhere to go. And that's why you need a fridge. So definitely, if this is something that's kind of going over your head, feel free to talk to me about this in a help session, all right? Or just, make note of these particular examples, because state changes sometimes almost feel the opposite. Or like they almost seem intuitively the opposite of what they actually are. All right, so freezing water is exothermic because the water itself has to give away its heat in order to be able to freeze. Endothermic processes require the heat to go into the system, so the system will get warmer, and you on the outside in the surroundings will feel cool. All right, so melting ice, this probably actually makes a little sense to you, because when ice melts, it cools off your drink. All right, so the ice, it's melting, the heat is going into the ice and letting the cool off the surroundings. Okay. Boiling water, though, is also an endothermic process. All right. The heat is going into the water in order to evaporate it. And this one sometimes might seem a little not intuitive because, you always have the stove going and it's warm as you boil water. But it's warm as you boil water because you have the stove turned on and the heat from the stove is going into the water in order to boil it. All right, so you're giving the water heat. You're putting heat into the water. All right? And there are some rare reactions that are endothermic. Nothing that you would necessarily be familiar with. But, like, I guess if you've ever used a cold pack. So, like, see, for me, I always did this if you got hurt at school. So I don't know if any of you guys went to in-person school when you were younger and maybe you had to go to the nurse's office and get a cold pack for a cut or a bruise or something. But there's a chemical inside those, so when, she cracks it and shakes it up, that starts the reaction and that's how it gets cold. So it's an endothermic reaction inside the cold pack. All right. So here is the trick to if this all made sense. What I want you to do is pause the video, see if you can determine these as being exo or endothermic, and then restart it up, and I will let you know if you were right. All right. So a burning candle. So me being in the surroundings next to a burning candle, I would feel warm. So that would be exothermic. Freezing water into ice. All right, so this one's tricky because the fridge, I'm artificially cooling the fridge. So I really got to think about the ice itself. All right, so the water is getting colder. All right, I know that's true because it's freezing. So if the water is getting colder, that must mean it is losing heat. So that is also exothermic. A reaction that results in increasing the surrounding temperature. So again, I'm in the surroundings, I'm feeling warmth. So that means that the system, the reaction itself, is losing that heat. All right, so again, exo. Exploding fireworks. All right, so if you've ever been near fireworks that go off, even if you do like the little ones, you can usually tell that there's a little bit of warmth given off by them. So that again is exo. All right, so boiling water. All right, so this one's a little tricky because when I do this on the stove, it's usually pretty warm. So you gotta keep in mind that that warmth, that's actually coming from my stove. So I'm giving that warmth to the water. All right, there's also, if you feel the steam itself is warm. So the water is getting warmer. So the heat's going into the water, that is endothermic. And that's it for this one.